The moment 3I Atlas passed Earth, nothing dramatic happened in our skies. There was no sudden flash, no strange signal, no visible spectacle that demanded attention. From the ground, it felt almost disappointing. But in science, silence is rarely empty. This quiet passage marked the exact point where real investigation truly began. As the object moved away, telescopes around the world subtly shifted their focus. They were no longer watching Earth or the point of closest approach. Instead, they followed the retreating path of an interstellar visitor, leaving our neighborhood behind. The direction mattered more than the moment itself. At this stage, the central question also changed. Scientists were no longer asking what 3I Atlas was. That question belonged to the discovery phase. Now the focus turned toward what it could still reveal as it continued its journey. Every data point collected after the flyby carried more weight, not less. The post-flyby trajectory is now tightly constrained by observation. Measurements from multiple instruments have reduced uncertainty to a minimum. What once looked like a wide range of possible paths has narrowed into a clear outbound direction. And that direction points unmistakably toward the outer regions of the solar system. Earth is now behind it. The encounter is over. But the journey is not. The most revealing phase may still lie ahead, far from our planet, where gravity, distance, and time begin to test what 3I Atlas truly carries with it. So after leaving Earth behind, where is it really headed next? "3I Atlas entered the most scientifically valuable phase of its entire passage. With the closest approach behind it, astronomers were finally able to lock down its trajectory with a level of precision that was impossible earlier. Radar measurements and optical tracking from multiple observatories converged, sharply reducing orbital uncertainty. What once required wide error margins now resolved into a clean, well-defined path through space. One of the most important confirmations came from its velocity. 3I Atlas is moving at a clearly hyperbolic speed, fast enough that the sun cannot bind it gravitationally. This is not a temporary visitor looping back around. Its motion confirms an interstellar origin that cannot be reversed, no matter how long we observe it. It will never become part of the solar system. Equally important is what scientists did not see. There is no evidence of gravitational capture by Earth, and no sign that the sun has altered its fate. The object passed through without slowing into a bound orbit or deviating in a way that would suggest hidden forces. Gravity behaved exactly as expected, which in itself is a critical result. As the refined trajectory emerged, another subtle detail became clear. 3I Atlas is gradually climbing away from the plane of the solar system. Instead of remaining aligned with the flat disk where planets orbit, its path tilts outward, reflecting a history shaped far beyond our stellar neighborhood. This geometry is one of the quiet signatures of its foreign origin. This moment represents what scientists call a clean data window. Outgassing forces, observational gaps, and early measurement noise no longer dominate the calculations. Many of the small discrepancies that fueled debate in the early days have now disappeared. What remains is a trajectory shaped almost entirely by gravity and initial conditions set long before the object ever reached our Sun. With the orbit now firmly established, uncertainty gives way to intention. The question is no longer where 3i Atlas came from or whether it will stay. Those answers are settled. The new focus turns forward. When the path is finally clear, what is the next scientific target that this interstellar traveler allows us to explore? As 3i Atlas moves farther from Earth, scientific attention naturally shifts toward Jupiter. This is not because Jupiter lies directly in its path, but because Jupiter represents the most powerful gravitational environment the object will encounter after leaving the inner solar system, with more mass than all other planets combined. Jupiter dominates the dynamics of anything passing through its sphere of influence. For small bodies like comets and interstellar objects, Jupiter acts as a natural scanner. Any object that passes nearby is subtly tested by its gravity. Even without a close encounter, Jupiter's gravitational field can reveal information that no telescope alone can provide. Tiny deviations in motion, changes in speed, or shifts in orientation can expose properties such as mass distribution and internal structure. This is why Jupiter is so valuable scientifically. Its gravity allows researchers to probe 3.1 Atlas without touching it. There is no need for impact or physical interaction. If the object is unusually dense, unusually light, or structurally fragile, those traits will express themselves through how it responds to Jupiter's pull. Gravity becomes a diagnostic tool. No other planet offers this advantage at the same scale. Saturn is massive, but weaker. The inner planets are too small to produce measurable effects at distance. Jupiter alone creates a natural laboratory where physics operates at planetary scale, for an interstellar object that will never return. This may be the last opportunity to extract certain kinds of information. This is also where anomalies would become hardest to hide. If 3i Atlas behaves exactly as predicted, it strengthens current models of interstellar bodies. If it does not, Jupiter is the place where that discrepancy would first become visible. A slight mismatch between prediction and observation here would carry enormous implications. That is why eyes are turning outward, not inward. Jupiter is not the destination, but it is the test. The remaining question is whether 3i Atlas will pass close enough for this gravitational experiment to matter, or whether it will slip through the outer solar system just beyond Jupiter's most revealing reach. Current orbital models paint a picture that is both reassuring and scientifically ideal. 3i Atlas is not on a collision course with Jupiter, nor is it expected to skim dangerously close to the planet. Instead, projections show a controlled passage at a distance that avoids extreme gravitational stress while still allowing Jupiter's influence to be felt in measurable ways. This balance matters. At the predicted range, 3i Atlas will experience tidal forces strong enough to test its physical properties. Gravity will tug on the object, subtly stretching and compressing it, but not violently enough to tear it apart. Unlike many ordinary comets that fragment when they pass too close to massive bodies, this encounter is expected to remain intact. That separation creates a rare observational advantage. Because the object is not being destroyed or dramatically reshaped, any changes that do occur can be interpreted as natural responses rather than catastrophic failures. Scientists can observe how a pristine interstellar body reacts to a strong gravitational field without the confusion introduced by fragmentation, shock heating, or explosive outgassing. In this sense, Jupiter provides a clean experiment. The environment introduces stress without overwhelming the system. There are no impact events, no surface disruption clouds, and no debris fields to complicate interpretation. What remains visible are the object's intrinsic properties responding to external gravity in real time. For researchers, this is close to an ideal scenario. The interaction is strong enough to matter, but gentle enough to preserve the signal. Few interstellar objects will ever pass through such conditions under such clear observational coverage. 3I Atlas offers a test that is both rare and precise, which leads to the deeper question: if Jupiter can influence 3I Atlas without destroying it, what hidden properties might be revealed there that Earth-based observations could never expose? At this stage, one of the most important unknowns about 3I Atlas is its true mass. Until now, mass estimates have been indirect, inferred from brightness, observed activity, and how strongly sunlight drives material away from its surface. These methods are useful, but they depend on assumptions about composition and structure that may not fully apply to an interstellar object. A strong gravitational field offers a far more direct test. As 3I Atlas passes through Jupiter's sphere of influence, its trajectory will respond to gravity in a way that depends on mass. If the object is heavier or denser than current models suggest, even slightly, its path will deviate in measurable ways. Tiny changes in speed or direction can reveal far more than months of remote imaging. If no measurable deviation appears, that result is just as powerful. It would imply that 3I Atlas is extremely light for its size, likely porous, loosely bound, and rich in volatile materials. Such a structure would align with the idea of a fragile body formed in a cold, distant stellar environment, rather than a compact rocky object. An unexpected deviation, however, would be transformative. It would force scientists to revisit assumptions about internal composition, density, and even formation history. A heavier than expected mass could imply unusual materials, compact layering, or internal cohesion unlike anything seen in solar system comets. What makes this moment especially valuable is that it cannot be repeated. 3I Atlas will not return, and there will be no second chance to run this experiment under the same conditions. Jupiter provides a single, fleeting opportunity to weigh an interstellar object using gravity alone. As observational precision improves, uncertainty shrinks. For the first time, mass estimates may reach unprecedented accuracy for an object born beyond our Sun. The question that remains is whether 3I Atlas will confirm our expectations, or reveal that it is far heavier than we ever imagined. As 3I Atlas travels farther from the Sun, the environment around it changes dramatically. Solar energy drops off rapidly with distance, reducing the heat available to drive activity on the surface. According to standard comet theory, this should lead to a steady decline in outgassing. The coma should thin, the tail should fade, and visible activity should gradually shut down as volatile materials stop sublimating. That expectation is precisely what makes this phase so important. If activity weakens exactly as predicted, it supports current models of how icy bodies behave beyond the inner solar system. But if 3I Atlas continues to show a persistent coma or a structured tail, then something unusual is at work. Sustained activity at large distances would imply a different emission mechanism. One not driven purely by solar heating. This is where Jupiter's location becomes crucial. At these distances, thermal effects from the Sun are minimal, allowing scientists to separate heat-driven processes from material-driven ones. Any remaining activity cannot easily be explained by water-ice sublimation alone. Instead, attention shifts to more volatile substances such as carbon dioxide, ice, carbon monoxide, ice, or fine dust release driven by internal structure rather than temperature. For 3I Atlas, this acts as a direct test of its composition. Models suggesting a dominance of carbon dioxide ice predict that some activity could persist far from the Sun, albeit in altered form. Dust-rich structures could also respond differently, producing faint but measurable signatures even as solar input weakens. Jupiter's region provides the clean background needed to observe these subtle effects without interference. Every small change in the coma or tail at this stage carries disproportionate weight. Variations in brightness, shape, or orientation may encode information about internal layering, porosity, and the physical history of the object before it ever entered our solar system. These are signals that would be impossible to interpret closer to the Sun, where intense heating overwhelms more delicate processes. If 3I Atlas remains active in this distant environment, it would suggest that interstellar objects may operate under physical rules more diverse than those inferred from solar system comets alone. It would point to formation conditions shaped by different stars, temperatures, and chemical reservoirs. The question is no longer whether activity fades, but what it means if it does not. Beyond gravity, the region around Jupiter introduces another powerful influence that 3I Atlas cannot avoid. Jupiter is surrounded by an intense magnetic environment filled with charged particles, radiation belts, and flowing plasma. This is one of the most extreme space environments anywhere in the solar system. And it fundamentally alters how small bodies behave as they pass through it. Cometary tails are especially sensitive to these conditions. Unlike the dust tail, which responds mainly to sunlight, the ion tail interacts directly with magnetic fields and plasma flows. Even subtle changes in particle density or magnetic orientation can bend, stretch, or reshape the tail in ways that reveal how material is being released and transported away from the nucleus. For an interstellar object, this interaction is unprecedented. 3I Atlas is not just responding to the solar wind, but to a complex planetary plasma system shaped by Jupiter's rotation and magnetic field. By tracking how the tail aligns, twists, or fluctuates in this environment, scientists can directly observe how material from a foreign stellar system behaves under planetary scale electromagnetic forces. What makes this especially valuable is that it requires no speculative assumptions. The physics of plasma interaction is well understood. The key is precision. If the motion and structure of the tail can be measured accurately, researchers can infer particle sizes, charge states, and release rates without inventing new theories. The environment does the work. The data simply needs to be read correctly. This effectively turns Jupiter's magnetosphere into a natural laboratory. There is no experiment to design and no instrument to launch. The conditions already exist. Operating continuously at a scale far beyond anything humans could replicate, 3I Atlas is simply passing through at the right moment to be observed. If the plasma environment around Jupiter produces unexpected behavior in the coma or tail, it could point to unusual internal properties, variations in cohesion, conductivity, or material layering might become visible only under these conditions. The interaction could expose structural weaknesses or internal complexity that gravity alone cannot reveal. The question now is whether this extreme environment will leave 3I Atlas unchanged, or whether it will uncover details hidden deep within an object that formed around another star. As 3I Atlas moves into the outer solar system, direct pursuit is not required for science to continue. Several spacecraft are already operating far from Earth, positioned in regions where their instruments can still contribute valuable data. These missions were not designed to study interstellar objects, yet their presence creates unexpected opportunities. What matters most is geometry. A spacecraft does not need to fly alongside 3I Atlas to observe it. A favorable viewing angle is often enough. From the right position, instruments can sample how light, charged particles, and radiation interact with material released from the object as it moves through space. These indirect observations can fill critical gaps left by Earth-based telescopes. Such measurements often focus on spectra rather than images. Ultraviolet signatures, particle detectors, and plasma sensors can detect changes that cameras would never resolve visually. These signals may appear abstract or unimpressive to the public, but they carry precise physical information about composition, ionization states, and energy transfer processes. This kind of science unfolds quietly. Data streams are recorded, calibrated, and stored long before any conclusions are drawn. There are no press conferences or dramatic images at this stage. The value lies in accuracy, not presentation. Weeks or even months can pass before researchers are confident enough to publish what they see. Because these observations are indirect, they are often overlooked outside the scientific community. Yet they can reveal how an interstellar object interacts with environments shaped by planetary magnetospheres and distant solar influence. These interactions help complete the physical picture of 3I Atlas in ways that direct imaging cannot. Much of what is being recorded now will remain invisible to the public for some time. Subtle shifts in particle counts, faint spectral lines, and small changes in radiation levels may already be stored in mission archives. What remains unclear is how much of 3I Atlas's story is already being captured, quietly and unnoticed, long before anyone recognizes its importance. When placed beside the two interstellar objects detected before it, 3I Atlas immediately stands apart. The first visitor, Oumuamua, passed through the inner solar system without ever encountering a massive planet capable of testing it after discovery. Its story ended almost as soon as it began, leaving scientists with unanswered questions and no chance for a second look under different physical conditions. Borisov offered more clarity, behaving much like a familiar comet. But its trajectory never carried it through a gravitational environment as dominant as Jupiter's. Observations remained largely limited to solar-driven activity and remote spectroscopy. Once it moved away, the opportunity to probe deeper physical properties faded quickly. 3I Atlas changes that pattern. For the first time, an interstellar object is being observed not only during discovery and closest approach, but also through a distinct post-encounter phase. Its outbound path through the outer solar system creates a kind of afterimage, where gravity, plasma, and distance strip away early uncertainties and expose more fundamental behavior. This extended observational window is something neither Oumuamua nor Borisov ever provided. When all three objects are considered together, a clear message begins to emerge. There is no single template for interstellar visitors. Their shapes, activity, composition, and responses to their environments vary widely. What once looked like outliers now look like early samples from a much broader population. This comparison quietly dismantles the idea of a standard interstellar object. Each one appears to carry the imprint of its own stellar origin, its own formation conditions, and its own journey through interstellar space. Similarities may exist, but they are no longer the most important feature. 3I Atlas does not simply add another data point. It reframes the comparison itself. Instead of asking how closely it matches what came before, scientists are now forced to ask how diverse interstellar objects truly are, and whether previous assumptions were ever sufficient to begin with. As data from 3I Atlas continues to settle into place, its impact extends far beyond the object itself. What is coming into focus is not just a better description of a single interstellar visitor, but the pressure to revise several foundational models that have guided astrophysics for decades. One of the first areas affected is how interstellar comets are thought to form. Traditional models are built largely on what we know from the solar system, assuming similar temperature gradients, material availability, and evolutionary paths. 3I Atlas challenges that assumption by demonstrating that comet-like bodies can emerge from very different stellar environments and still remain intact across interstellar distances. Closely tied to this is the question of how material is distributed beyond our solar system. Current models of debris disks and planet-forming regions rely heavily on indirect observations of distant stars. Interstellar objects provide a rare physical sample, allowing those theoretical distributions to be tested against real matter that has crossed from another system into our own. Interactions with giant planets form another critical layer. Jupiter serves as a stand-in for gas giants around other stars. How 3I Atlas responds to its gravity offers a proxy for understanding how interstellar debris interacts with massive planets elsewhere in the galaxy. This has direct implications for planetary system stability and long-term evolution. Structural assumptions are also under review. Many models presume a certain balance between strength and fragility in small bodies. If 3I Atlas proves more resilient or more delicate than expected, it will force scientists to rethink how such objects survive ejection from their home systems and endure the harsh conditions of interstellar space. These revisions ripple outward into exoplanet science. The formation and evolution of planetary systems cannot be separated from the behavior of the smaller bodies within them. Adjusting these models alters how scientists interpret observations of distant worlds, debris disks, and planetary architectures. What makes this especially powerful is scale. One object, carefully observed, can trigger dozens of new studies across multiple fields, not because it is extraordinary in size, but because it carries information from beyond our solar system. The deeper issue is no longer whether 3i Atlas fits existing theories, but how many of those theories must now be expanded or rewritten to accommodate what it reveals. As 3i Atlas continues to move away from the Sun, it might appear that its scientific relevance is fading with distance. In reality, the opposite is true. The moment of closest approach has passed. But the data phase is only beginning. What has been collected so far forms the raw material for years of careful analysis rather than immediate conclusions. Interstellar research unfolds slowly by necessity. Measurements gathered during a brief encounter must be calibrated, cross-checked, and revisited repeatedly as models improve. Subtle patterns often emerge only after datasets from different instruments and observatories are compared side by side. What seems unremarkable in isolation can become significant when placed in a broader context. This is why post-encounter analysis matters so much. Many of the most important insights do not appear in the first wave of publications. They surface later, when early assumptions are challenged and discrepancies are examined rather than dismissed. Interstellar objects, by their nature, resist simple explanations. Scientific progress does not follow moments of spectacle. It follows depth. Each year brings refined techniques, better simulations, and new theoretical frameworks that allow old data to be interpreted in new ways. The same measurements can yield different conclusions as understanding evolves. This slow accumulation of insight is a defining feature of interstellar research. Unlike recurring solar system objects, these visitors do not return to offer clarification. Everything must be extracted from a single passage, making patience and precision essential. The departure of 3i Atlas does not mark an ending, but a transition. Its physical presence may be diminishing, yet its influence within the scientific community is just beginning to unfold. The real uncertainty lies in whether we have already heard everything it has to say, or whether its most important messages are still waiting to be recognized. 3i Atlas quietly reinforces a lesson that astronomy has been approaching for decades. The solar system is not a universal standard. The materials, structures, and behaviors we observe around our sun represent only one outcome among countless possibilities shaped by different stars, disks, and formation histories. Evidence from 3i Atlas suggests that matter formed elsewhere can follow rules that diverge from familiar patterns. Its activity, composition, and structural responses do not align neatly with expectations built from solar system comets alone. This does not mean those models are wrong, but it makes clear that they are incomplete. other stellar systems operate under different conditions. Variations in stellar mass, radiation output, disk chemistry, and evolutionary timelines naturally produce objects with distinct properties. 3I Atlas carries the imprint of those differences, offering a rare glimpse into processes that cannot be observed directly around distant stars. This perspective reshapes how we think about scale. The solar system, long treated as a representative example, is better understood as a single data point. Interstellar objects reveal that our local environment may be more specialized than previously assumed. The presence of 3I Atlas also hints at abundance. Interstellar space is likely filled with fragments ejected during planet formation across the galaxy. Most pass unnoticed. Too small, too faint, or too distant to detect. What we observe may be only a tiny fraction of what moves between stars. In that sense, 3I Atlas is less an anomaly and more a signal. It demonstrates that the galaxy is rich with material shaped by countless stellar histories. And as detection methods improve, this may be only the beginning. If one object can reveal so much, it raises a quiet but unsettling thought about how much is passing through our cosmic neighborhood without ever being seen. 3I Atlas is already shaping how scientists prepare for the next interstellar visitor. Its passage has exposed both the strengths and the limitations of current observation strategies, prompting a shift from reactive discovery to deliberate readiness. New generations of telescopes are being optimized with interstellar objects in mind. Faster survey cadence, wider fields of view, and improved sensitivity are designed to detect faint, fast-moving bodies earlier in their approach. Early detection extends the timeline for planning and transforms chance encounters into coordinated campaigns. Equally important is a change in follow-up strategy. Rather than focusing almost entirely on the moment of closest approach, researchers are placing greater emphasis on the outbound phase. Post-flyby observation is where uncertainties shrink and deeper physical properties emerge. 3I Atlas has demonstrated that this phase deserves structured, long-term attention. Giant planets are also moving into earlier planning stages. Jupiter and Saturn are no longer treated as distant background actors, but as potential diagnostic tools. Their gravitational and plasma environments offer unique opportunities that can be anticipated and incorporated into observation schedules well in advance. This shift reflects a broader mindset change. The goal is no longer to be surprised and then react, but to anticipate and prepare. Interstellar objects will not announce themselves with certainty, but the scientific response does not have to begin from scratch each time. In this sense, the most lasting contribution of 3I Atlas may not lie in any single measurement. It lies in how it has altered expectations and planning. Its legacy is a more mature, forward-looking approach to interstellar research. The question now is whether, when the next visitor appears, we will truly be ready to meet it on our own terms. For all the attention surrounding 3I Atlas, its most important contribution is defined by what it did not do. There were no signals, no flashes of light, and no dramatic events that demanded immediate interpretation. In a media landscape driven by spectacle, this absence can feel anticlimactic. In science, It is often a sign of clarity. What 3i Atlas delivered instead was data. Quiet, incremental, and precise. Measurements collected over weeks and months now sit in archives, waiting to be analysed with care. This kind of information rarely makes headlines. Yet it is the foundation on which understanding is built. Scientific progress rarely arrives in moments of excitement. It emerges through patience, verification, and repetition. The most meaningful discoveries are often the ones that unfold slowly, as patterns become visible only after careful comparison and long reflection. 3i Atlas does not provoke fear or urgency. It invites comprehension by behaving largely as physics predicts. It strengthens confidence in existing models while still leaving room for refinement. That balance is a hallmark of mature science. Understanding moves at a different pace than attention. It resists deadlines and ignores public expectation. But once achieved, it endures. Insights gained from 3i Atlas will inform research long after the object itself has faded from view. The true test is not whether the encounter felt dramatic, but whether we are willing to wait for its meaning to fully emerge. The value lies not in immediate answers, but in whether we have the patience to let science speak on its own time. As 3i Atlas continues beyond Jupiter and fades into the vast space between stars, its journey becomes something we can no longer follow directly. It will not slow down. It will not turn back. There will be no second encounter. No opportunity to correct missed measurements or ask new questions in real time. This brief passage was the only chance we were given. And yet, it does not truly leave us empty-handed. What remains is embedded in data, in models. And in the subtle ways, this object has already reshaped how we observe the universe. Long after 3i Atlas disappears from our instruments, its influence will persist in research papers, simulations, and future observation strategies. Its physical presence may be gone, but its scientific footprint is permanent. 3i Atlas does not offer a final answer about the cosmos. It does something more important. It sharpens our questions. It reminds us that the universe is not obligated to be familiar, and that understanding often begins not with certainty, but with humility. Each interstellar visitor carries a fragment of a much larger story, one that no single encounter can ever complete. What comes next depends on us, on whether we choose patience over spectacle, curiosity over conclusions, and depth over noise. If you want to continue exploring these quiet frontiers of science, where data speaks slowly and meaning unfolds over time, this channel is built for that journey. Subscribe to support this work, and stay with us as we follow the next questions the universe places in our path. Because when the next interstellar object appears, the real question will not be what it is, but whether we are finally ready to listen